Okay, so we are now in Unit 18, Test for Correlation, Section 10.1. We start with a couple of definitions. First, let's define bivariate data. Those are data values that come in pairs. So the first data value in the pair is called the explanatory variable. It is denoted using X, and it explains the changes or variation that occur in the other variable. The explanatory variable is also referred to as the independent variable. The second data value in the pair is called the response variable. It is denoted using Y, and it measures the outcomes that result in changes to the explanatory variable. The response variable is also referred to as the dependent variable. So as an example, an educator wishes to examine research regarding the amount of sleep the night before an exam, how that affects performance on the exam for a student. The resultant data will have the following form. It's a form of an ordered pair. The numbers are encased in parentheses. The first number is your X value, your explanatory variable, and that is 6. 6 represents the hours of sleep the night before the exam. The second number is the response variable. That's the score that the student earns when they take the exam out of 100 points. Let's take a look at a list of bivariate data. Okay, so we have the data represents the following. It's the age-related deaths in New York City from the year 1981 to 1994. And the deaths are in hundreds. So 1 represents 100, 2 represents 200, etc. So we have a few questions that are posed to us regarding the data set. First question, why would we say that each of these variables is a quantitative variable as opposed to a categorical variable? Quantitative because both data values are numerical. Thus, you can perform some basic operations on these values. Categorical, those are values that are typically nominal, or you can arrange values in categories. Second question, which is the explanatory variable and which is the response variable? The years are the explanatory variable, the number of deaths, the response variable. So as we can see, as time goes by, the number of deaths are increasing. Okay, now what we'll do is we are going to construct what's called a scatter plot using this given information. So a scatter plot is found by plotting points on a coordinate system. This axis is our x-axis. That's where we put down the years. This axis here is the y-axis. That's where we put down the number of deaths. And we try to use consistent intervals of numbers. So for deaths, we go by tens. Years, it's going to go by every 2 years. And we just plot the points. So for 1981, there was 1 death. For 1982, there was 2. Actually, it's 100 and 200, but we're just using smaller numbers to make the graph easier to read. And then we can see that we do have a pattern that's being formed. Now we're going to examine the pattern. So when we examine the pattern, we look to see the direction, the form, and the strength. Well, the direction, is it positive increasing, negative decreasing, or neither? Well, in this case, the points are increasing. As time goes on, the deaths are increasing. So we say that the pattern is positive, meaning it has a positive slope. The direction, so that's going to be the direction of our pattern. The form, is it linear or curvilinear? Well, it's linear, because linear just means it has the shape of a line, and as we can see, we do have a linear shape for this data set. And then, so that's our form. The strength, is that linear relationship very strong, weak, fairly strong? I would say it's a very strong linear relationship, very strong. And then finally it says, are there any striking deviations, any outliers? No. An outlier would be a value that would be out of the sequence. And I don't see any values that fall out of the sequence. So there's no outliers. And then we look at some other examples of scatter plots. If we look at this example here, we would see that there's no linear relationship. We can't tell if it's positive or negative. Here we have a stronger linear relationship. It's not a perfect one, but it's pretty strong. It's positive because it's increasing. Here I would say this is a fairly weak linear relationship. And so what we use the scatter plots just to sort of help us get a basic understanding of the form of the pattern of the linear relationship between x and y. Now we're going to look at the complete set of data from 1981 to 2010, and we can see that from 1981 to 1984, it's linear, but then obviously because of some improvements in drug and care for people that have AIDS, we can see that the number of deaths died. And so this type of graph is, the complete graph is called curvilinear because once you look at the complete set of data, it's not a linear graph. And there's no way of forcing this graph to be linear. Now, to measure that relationship between x and y, we have to compute what's called the correlation coefficient. And we will be using what's called the sample correlation coefficient, which is denoted as R. So when R is 1, as we can see in this example here, we have a perfect linear relationship. All the points line up in a perfect pattern, and you form a linear pattern. Now, when R is less than 1, but still positive, it may not be as strong as in this first example. We would state that R would be 0.75. If R is scattered in this manner, where there's no linear shape, then R is 0. And then if R is -1, that means the values are decreasing. We have a perfect linear shape, but now the values are decreasing, then R is -1. A graph that encapsulates the values of R would be the R bar. The minimum value is -1, the maximum is 1, the center is 0. We have two critical values. If R falls in this region, we say there's a strong negative linear relationship. If it falls in this region, we say there is no linear relationship. If it falls in this region, we say there's a strong positive linear relationship. Now we can go ahead and set up a claim to test for correlation. To do this, we have to use not the sample correlation coefficient one, but the population correlation coefficient, which is denoted with the Greek letter rho. So for H0, we have rho is 0, that's the claim. That just means there's no linear relationship. For H sub 1, we have rho is not equal to 0. That means that there is a linear relationship. So whenever we set up a claim, we're going to use this notation here. So let's look at an example. Assume that Brandon Ramos would like to study to see if there is a correlation between the amount of coffee consumption per week and the amount of sleep per week. He randomly surveys 10 people regarding both variables. Which variable is the explanatory variable? The amount of coffee consumption. Which variable is the response variable? The amount of sleep. Coffee is affecting sleep. That's the assumption here. So the data, we collect our data, so Brandon has the data available to us. First, we construct our scatter plot. So we put the number of cup of coffee on the x-axis, the amount of sleep per week on the y-axis, and then we can examine the pattern. We can see that it's fairly linear. It's negative because it decreases. and it's I would say that it's somewhat strong. Not very strong, just somewhat strong. Our second step would be to state our claim and determine H0 and H sub 1. Well, this will never change in Chapter 10. The claim will always be the same. Rho is 0 is a claim. Rho not equal to 0 would be H sub 1. We next have to compute our degrees of freedom. To compute degrees of freedom, since we now have two variables, it's n minus 2, where n is the number of pairs. We draw the R bar and we look up the critical values for R. Table I will be provided to you. In this case, we'll be using 0.05. So the R bar, degrees of freedom is 8. We go to table I, we go down to level 8. Alpha is 0.05, so 0.632. 0.632, and we also have, by symmetry, negative 0.632. Now we have to compute R. I'm just going to strongly recommend that you use your calculator to compute R. However, I will walk through an example to demonstrate how we would use the formula for the computation of R. So what we typically do is we have to add some columns to our XY column. So the first column we add is the X times Y column. So we have to multiply each X value with each Y value to determine this column. The next column is we square each of the X values. And then the final column is we square each of the Y values. Finally, we find the sum of each column. It's these sums that will help us determine R. Remember, n is the number of pairs, n is 10. So the formula for R, in the numerator, we have n times the sum of the xy column minus the sum of the x column times the sum of the y column. Divided by the square root. In our first bracket, we have n times the sum of the x squared column minus the sum of the x column squared. Second bracket, n times the sum of the y squared column minus the sum of the y column squared. So we insert these values into the formula and calculate. We get negative 0.962. However, as I mentioned previously, you can just type this data into your calculator and it will compute R for you. So that's my recommendation. I will avoid trying to use this formula. And I do have some videos that will show you how to calculate R with your calculator. And so now let's examine our results. We have negative 0.962. That falls in the critical region. So we reject H0 whenever a test point falls in the critical region. Reject H0. And we do have a little summary chart here that just states there is a strong linear relationship. So whenever we reject H0, we always state there's a strong linear relationship. If we do not reject H0, there is no linear relationship. Okay, and I'm just stating here, just reminding people to use their calculators. There's a couple of examples for people to try. Let's do one more. So let's say that we have, once again, some bivariate data. This time it's, let's say, hours of cardio per week. So we look at the hours of cardio per week. That's going to be our X value. Our Y value will be the lifespan in years. So we want to see if there's a correlation between the amount of cardio a person does per week and their lifespan. So once again, we draw the scatter plot. First step, x-axis, we plot our points, X will be the hours of cardio, y-axis will be the lifespan of an individual. Our claim, that's always the same and never changes. Degrees of freedom, 10, there's 10 data values minus 2 is 8. We look it up in table I. We end up with the same critical values. Now we compute the correlation coefficient, and as I mentioned before, we type it into our calculator, and we end up with positive 0.935, which falls in the critical region. We check H0. There is a linear relationship. And we are done with this unit.